Welcome to the second video in the series, The Learning Networks of the Brain. In this video, I will focus on the recognition networks. I'm Ruth Bomar. A lot of my material comes from the book, The Teaching Every Student in the Digital Age, Universal Design for Learning by David H. Rose and Ann Meyer. The recognition networks located at the back of the cerebrum, cerebral cortex right back here, enable us to identify and interpret patterns of sound, light, taste, smell, touch, which are our five senses. In addition, I'd like to add two more senses, the vestibular, which are receptors in our ears, which provide information about the body's movements, balance, and coordination to the brain. The other one is the position sense, proprioception. These are receptors located in our muscles and our joints and give us information about the position of our body in space. If you close your eyes and I ask you to touch your nose, you can. This ability to know where your nose is in space without even looking is proprioception. A huge amount of information is coming to our brain through our senses. These networks enable us to recognize voices and faces, letters, words, complex patterns such as author's style and nuances, as well as abstract patterns and concepts such as justice or even calculus. Take, for example, this painting by Russian artist Repin in 1888. You probably recognize the objects depicted in this painting: people, doorways, the floor, the wall, furniture. You can identify parts of these objects, such as ears, doorknobs, table legs. Even though these objects are partially hidden, others are at odd angles or in poor light, yet your recognition networks can determine what these objects are. Look at the table, look at the chair right here in the foreground. You could recognize this object as a chair without seeing the features normally associated with chairs, such as four legs and a seat. You can also recognize the chair as part of the category of furniture. Recognition seems simple, but is actually an incredibly complex feat. So how does the brain accomplish this complex work of recognition, all in just a microsecond? If we look at a PET scan, we can see visual stimuli activates one area of the cerebral cortex, and auditory stimuli activates another part of the cerebral cortex. The task of recognition is distributed laterally across brain regions in parallel. Each area is specialized to handle different components of the recognition process. All the sensory input is distributed to different locations in the brain to be processed. Additionally, the input is further processed. For example, your elements like vertical lines, or horizontal lines, or diagonal lines, color, movement, are all processed in physically discrete areas of the brain. I'm going to call these specialized areas of the brain modules. Each area has tissue that is finely tuned to process the type of input extremely efficiently. Recognition is quick and efficient because all the modules work in parallel. Our brain processes and coordinates information that is distributed throughout our recognition networks in less than half a second. All the modules are interconnected through multiple pathways. This means that visual, auditory, olfactory, and tactile recognition all influence one another. This is why a sound or a smell can bias our interpretation of a visual pattern. The distributed nature of recognition profoundly impacts individuality. Everyone's pathways in the recognition network are unique. The implication to the learner is this: we need to learn. When we learn something, we need to stimulate as many pathways, as many recognition networks as possible. The The pathways of all this processing of sensory input are organized in a hierarchy, bottom up and top down. If we use vision as an example, let's look at the image again of the unexpected visitor, and we see particular sensory features. All these details. We see the diagonal boards on the floor. We see the pattern, the wallpaper. We see the angle of the open door. We see light coming in. We see all these details of this picture. This is bottom up. Now, in the process of looking at details, poor lighting, blurry images, or even slurred speech can impede the processing. Simultaneously, the brain makes use of higher order information, such as the background knowledge, context, and overall patterns to help us with recognition details. This is called top-down. So in this picture, we see the position of this woman's body tells us that she's probably just got up. The direction that everyone's eyes are looking at the man, he's probably the unexpected visitor. The angle that the light is coming in through the window tells us the time of day. The apron on the lady opening the doorway tells us that she's probably a servant. Now, think about learning to read. Letters are recognized by their features and joined together to form sounds and words. But research has shown us that it is easier and faster to recognize letters in the context of words than in isolation. This phenomenon, termed the word superiority effect, occurs because familiarity with the larger pattern constrains the bottom-up process of individual letter recognition. And this leads a reader to rely more on his or her expectation of what letters come next, and less on the actual visual features of these letters. So in this picture right over here, we see this B if we're reading the letters A, B, C, but we see a 13 if we're reading downwards, 12, 13, 14. So the context is influencing the identical, this figure right here, which is actually identical. In one situation it's a 13, in another situation it's a B. This is why proofreading is so difficult. We miss errors because our word expectations are so powerful that they influence how we see the individual letters. The use of context and meaning to predict what is coming next is a familiar example of top-down processing used in reading. John Miller, in his book Brain Rules, describes the individual differences in recognition networks. If we use the interstate highway system as an analogy, we all have the main interstate highways in common, but we differ in the exits, their location, the number of exits, and the intricacies of the neighborhood streets. Although human brains share the same basic recognition architecture, our recognition networks vary in connectivity, physiology, anatomy, and chemistry, making my brain slightly different than yours. Our patterns of recognition are as unique as fingerprints. For example, when most people recognize an object visually, the back part of their brain lights up, showing increased activity. However, the exact magnitude, location, and distribution of that increased activity varies from person to person. The active area in the cortex might be larger or smaller, more localized to the right or left hemisphere, or it could be widely or closely distributed. These differences explain strengths, weaknesses, and preferences. In my next video, I will address the strategic networks which enable us to plan, organize, and monitor. Look me up at www.ruthbomar.com or follow me on Facebook, Ruth Bomar, Academic Coach.